Okay, hello everyone. I know your minds are already set on the midterm on Monday, but we have to go through a lecture today before we get to that midterm. We have already covered all the material that we need for that midterm. That being from chapter 1 to chapter 4, i.e. the robustness analysis, if my numbering is correct. And today we're going to begin a brand new chapter. It's called static modeling, followed by another chapter. Number 7 is called dynamic modeling. Let me just click on this. All right. So you're going to understand different types of relationships, mainly the three ones that exist: association, aggregation, composition, and generalization. And we're going to understand static modeling, not just as class diagrams, but as class diagrams representing physical classes and as class diagrams representing entity classes as well. And finally, we're going to look at the system context model. I know we've already covered system context modeling and requirements engineering last year, but we're going to look at it in a little bit more detail this time around. It's not going to be a big part of this course, all right? But it is something that we're going to just revisit briefly towards the end of this chapter. Okay. Now, before I talk about static modeling per se, any system, like this thing that I have in my hand, it can be viewed from different perspectives, okay? Obviously, anything static can be looked at from a frontal view, side view, an upper view, and bird's eye view, zoomed out view, zoomed in view. And each one of those views gives us a little bit more information about the system that I'm looking at, okay? So this view over here tells you a lot of information about the mouse clicker that I have in my hand, okay? Tells you the height, tells you the width, but it doesn't tell you the depth. Only when I flip it as such, now it can tell you the height and the depth, but it doesn't tell you the width. But anyway, when you add up all this information together, then you get an idea of what the entire system is like, all right? The key thing, all this information that we're getting from all of this perspective, they're talking about the same system. So ultimately, everything should be consistent at the end, okay? So when I have the mouse pointed in front of me and I see it at a certain height, say 5 centimeters, there's no chance that when I flip it to the side, then its height suddenly is 4.5 centimeters, okay? It has to be exactly the same because we're talking about the same system here, all right? Even when you zoom in and you zoom out, it's fine to have different levels of abstraction, okay? When you zoom out of the map of the city of Riyadh, it's fine not to see the neighborhood street, okay? But for example, you might see the Northern Ring Road. When you zoom in, it doesn't make sense that suddenly that Northern Ring Road would disappear just because you zoomed in, okay? Then that's just inconsistent viewing of the same thing, okay? Now, when it comes to software systems, we have multiple perspectives. The first two that you see on the slide over here in the red and the pink are perspectives that we've actually already covered. The first of which is the external perspective, okay? How is it that the outside world is looking at it? So as the system is being displayed as a black box, which is what we've been doing in our requirements engineering when we looked at the system as a black box and we're focusing more on the external. Okay, that was the whole purpose of that exercise. If you remind me, if you remember me saying that last year, okay? So that's already the external perspective. Give me a little bit more information, okay? Now, next thing, we looked at the interactive perspective, the interaction between my system and the outside world. And we did that with, remember from 225? Use case modeling, yes, right? Remember, yes, use case modeling. And we talked about that use case modeling was all about this boundary level information. Remember that slide with the zigzag thing that was happening? Okay, that's all interaction with the system perspective, okay? Now, what we're gonna be looking at more in this course is what's inside the system. And we're gonna look at what's inside the system, all right, from two perspectives, a static perspective as things stand and how they relate to each other, okay? And from a dynamic perspective, as things move and how they interact with each other, in order, of course, to execute and deliver some sort of a service to a user. All right. Now, let me step out of here just for a second. I just want to pull out a white screen. There we go. Make sure that it is shared. I always make that mistake. There we go. All right. So we start off saying, okay, here it is. This is my system. Remember 225 stuff. This is my system. And the external perspective, when we did system context modeling, we were trying to figure out the world outside, just to realize who our actors were. We realized we have this guy, this person, that person, and so on. Okay, those could be systems. And obviously, we're not talking about particular people, instances like Hassan, Ibrahim, and so on. We're talking about roles, okay, being professor, a student, and so on, or a customer, or waiter, and so on. Okay, now the next thing we looked at was the interaction perspective. Now we know these people, they want something from us, okay? So what we looked at was, here's my system. And I know that there's gonna be some boundary level interaction until something is delivered at the end, okay? Now, the use case is not describing what's going on inside over here that makes these interactions a reality, okay? In matter of fact, if I actually look a little closer into this, what's really happening is that the user provides an input. There's some computation that happens outside that results, that causes this to happen, okay? We actually begin by describing this, followed by that. And we leave it up to the designer to say, write the necessary code and design to make this a reality, and so on and so forth until we have delivered that service, okay? Now, in order to do this part over here, in order to do that part over there, I need to create code for it, okay? That's really my internals of my system here. That's all right. All right, so for internals of my system, there is different components, okay? Kind of like in a bicycle, there's different components. There's the gear, there's the bolts, the nuts, the needle, whatever it is that exists, okay? And we first, and this is what mechanical engineers do, and matter of fact, anybody in mechanical engineering would study first, is what you study the statics first, okay? You know the components, how they interact with, how they relate to each other, okay? So in an actual bicycle, you would have one wheel at the front, one wheel at the end, you know, then you got the frame, okay, excuse my very bad drawing, and so on. And then the frame puts certain pressures on this, and then they design this first as it's standing, not doing anything, all right? They're not gonna design it as it's moving. You just gotta, first thing is gotta be is that what is it like as it's standing? And then first of all, I gotta think of is that the body of the bike is at the top and it's putting weight on the bicycles at the bottom and so on. Again, when it comes to the software world, what I'm looking at as I'm analyzing a particular domain, like say a university domain, I look and say, okay, I see a student, I see a professor. So here's my student, here's my professor, here's my course, here's a payment, here's student record, and so on and so forth. And I realize there's certain things that relate those things together, okay? Now later on we can create subsystems and so on and so forth, that's fine, okay? But before I even think about the actual activities that happen inside the university, which is students registering classes, students dropping classes, students getting the exams and solving the exams, and professors teaching those courses, professors assigning, these are the actual activities. There is nonetheless, all of these activities are happening on a basis, on a static basis, that there's a professor, there's a student, we're related through a course, okay? Maybe we can supervise you, in some sort of a project. And these are the entities that exist and the relationships with each other. Okay. So one of the things that we are not involved as professors is, for example, the financial aspect between you and the university. That's none of our business. Okay, that's not all we get at the end is these are the students who are registered in that course, and that's it. Okay, so we set those relationships first, and then we start to set the dynamics. Okay, so we put down the you know, through the domain classes, and the next thing I realized, I said, well, we had a whole bunch of use cases before, and these are what I wanted to have happen. Then next level, I'm gonna discuss the dynamics of how things run inside. And as I'm doing the dynamics, I realized I need a little bit more classes. Okay, I go back and I add them to my static perspective. Okay, I needed this class, and those tend to be what we call solution-oriented classes. So we began with domain-oriented classes. No inventions here. There's no ingenuity, just what I'm seeing from my domain I wrote down. Then when I started to create the actual functions and functionalities, I realized maybe I need a little bit more classes to facilitate those solutions being delivered. Created extra classes. Those extra classes, nonetheless, are gonna need to be programmed. And so you end up with a detailed view from a static perspective, which you then look at in a UML diagram, and then you go ahead and program. Okay, I know you've done a little bit of UML modeling in the lab of 225. Did you? Right? UML class diagram modeling. Towards the end of the year, it was all Corona and all that stuff, but I'm pretty sure you know that something stuck from that time. Okay, we'll revisit this. This is going to be the main topic of this chapter, inshallah. Okay, but this is how it goes. It start off with the static. What are the things that we have? All right. And then we realize, okay, we got the use cases. So now we got to create the functions. As we're creating the function, we realize, oh, I need to create that class and this class and that class too. Then we go back, we add them to our original class diagram. And then that's the one we take and we go and program it. All right. And obviously, as we're programming it, we're not just programming the classes, but we're programming the classes with the methods and the functions and so on, according to the behavioral aspects that are written in multiple different design perspectives. Could be something like sequence diagrams, activity diagrams, state charts, collaboration diagrams, all this fun stuff. And that is going to be the focus of our next chapter, not this chapter. Okay. Now, again, the difference between what we're doing in this course and what you were doing in the lab of 225, the lab of 225 is just to get your hands experience with, and your eyes experience with seeing a UML diagram, sequence diagram, activity diagram, and so on. Creating those diagrams. I'll need to have you those ready in your mind before we started off this course. The main difference is that in this course, okay, we're actually showing you how to design rather than just this is notation and this notation rules, and here's how you do a box, and here's how you do a stickman figure. You're gonna get to actually learn how to design and put this and have a systematic way in design. Kind of like what we've been doing in robustness diagrams, okay? It wasn't just here's 3 little types of circles and a stickman figure, do everything you're on your own. No, we had a systematic way of doing things, okay? So back again to the slides. The focus of this chapter, as I said, is the structural perspective. So number 3, the green one. Okay, we already covered 1 and 2 in 225, and now we're going to be covering the green one in this course. Let me just do this over here. All right, so structure models, they display the organization of the components that I have and their relationships, okay? Not how they interact with each other, okay? This is very important. I'm only explaining that there is a dependency between student and professor. student and tuition system, payment system, okay? And I'm showing through this that there's no relationship between professor and the payment system. Okay, that's none of our business, okay? Structured models, they're static. They show the structure of the system design. You create the models when you are discussing and designing the system architecture, okay? It goes a little bit, obviously you have to create an architecture first, okay? That precedes rather than, you know, just saying, oh, I got a student, I got so on and so forth, because then I gotta realize, where do I put these things, okay? Where do I place those classes? So those classes may be at the server, those classes will be at the client and so on. So the architecture design comes before that. Later on, like I said, the behavior models come in as we're looking at the use cases to see how those classes actually interact with each other, much the same way when we were doing the finger follow approach in our robustness diagrams, saying this class talks to this class, talks to this class, comes back to this class, talks to, we're doing the same exact thing, okay? The good thing about robustness diagrams is that the notation is simple. So it leaves a lot of your mind free to think about design, all right? Think that was hard? Had you done it immediately through, say, sequence diagrams, it would have been a lot harder, okay? So UML gives us use case diagrams, sequence state, activity diagrams, and class diagrams. UML diagrams has become the de facto modeling language. De facto kind of like means the default, the golden standard now when it comes to system modeling. There is some variation for this. For example, there's something called SysML, system modeling language, but it's really from the same family. And all of them fall under the umbrella of something called OMG, Object Management Group, or Object Modeling Group, if I remember correctly. And UML wasn't the first, okay? There were modeling notations that came before that, okay? So don't think that modeling is UML and UML is modeling and that's all there is to it. No, there was actually things that existed before that. Matter of fact, we've seen one of those. Remember the data flow architecture that we had that we looked at, and the types of architecture patterns at the beginning of this course? Okay, data flow diagrams, DFDs, are not a UML type of diagram. CFDs, control flow diagrams, also not a type of UML diagram. ERPs, entity relationship diagrams, also as well, tends to be quite common in database modeling, not part of UML, okay? Matter of fact, UML itself was created by three guys. They call them the three amigos, and each one of them created one or two of these diagrams. For example, I remember a guy called Ivar Jacobson. He's the one that created use cases. But then those three guys came in and they looked at it and they said, well, together, our diagrams can provide a suite of diagrams to cover the different perspectives. And that's where the word unified modeling language, the word unified comes into place in UML. Okay, the letter U comes in unified, and then they brought this guy's diagram and that guy's diagram and the third guy's diagram, and together they created UML. But like I said, they're not the first, but now they're more or less the standard, okay? Something in particular like state chart diagrams, which we're going to be covering next chapter. State chart diagrams, there is many different notations that do the same exact things, okay? Finite state machines. UML has a version of it called state charts. I'm seeing a lot of people like dozing off in the, you know, has it been a long day or something? It's the first time I see you like dropping, you had a midterm, yeah, that's what I expect. All right, so I had less sleep last night, huh? All right, well, I'll try to make this as interesting as possible. I mean, what I do is I increase the volume a little bit every time I see the eyes going, then just, I count how many heads are dropping, and I was like, 1, okay, or 2, 3. Don't think I don't see you. I see you loud and clear, but I don't like to like bug you about it, but but I'm seeing a lot more heads dropping this time than it has in previous lectures, right? Class diagrams describe the class in terms of the system in terms of classes and their association. They're the only static modeling. Is really a natural way of reflecting the real world entities that are manipulated by the system. Big advantage that came about from the object-oriented paradigm, that we can actually code using the same terminology that we're seeing in the world. So you actually see something called student.java and professor.java, whereas back in the day, it was all stack and processors and registers, and nothing is actually saying student at any point. So you would really be easily fooled if somebody told you that this code is talking about what the student is actually doing. All right. So that in itself is a luxury we've come accustomed to, because the first time you get exposed to programming was through object orientation and creating those class names, but it actually wasn't like that. It wasn't easy as such at all. Okay. Class identification is difficult and requires a deep understanding of the application domain. Okay, now here I am. I keep saying student, professor, and all that, because we know this domain very well. If you go to a restaurant, it's the same thing as well. But you might end up going to, say, a water purification plant. Pretty much beyond water and the word purification, you have no idea what's going on inside of there, right? You need to actually have some sort of a chemical engineer to talk to, an environmental engineer to talk, or civil engineer to talk to tell you what exactly is happening over there, okay? Now, they're not software engineers. It's our job to create those classes. So to actually look at something in that water purification plant and realize, okay, that's going to be a class. That's going to be a class, and so on, right? That is not easy, okay? Somebody could come out of this world, come to this university, see you sitting, and see me standing over there, and like, well, say, well, okay, them and the person who's standing over there, they all got legs and arms, and so they're the same class. So they're going to call a class called human. That's not good, okay? Because you need to identify the concept of a student, and that it's a separate concept from a professor and so on. Classes reflecting domain entities tend to be reusable across systems. That's very true, okay? Class called course, pretty much going to find in every university a class called course somewhere. The UML is a standard representation. I just talked about this a moment ago. It has become an effective standard for object-oriented modeling. All right, now let's focus a little bit at the notation, okay? So class diagrams, you've created it. I know you did, to some extent. We're just going to do a bit of a refresher, but a deep refresher this time. The notation of a class is a big box like that, okay? This, what you see, is not three triangles on top of each other. That's just one big box that is split into three compartments. The first is the name. The second compartment is the attributes. The third is operation. Now, in a different community, they call this the file name. They call the middle part variables. They call the last part functions. Okay, tomato, depending on which community you're talking to. So if you're talking with UML people and designers, they're like, yeah, attributes and operate. If you talk to programmers who don't believe in modeling, they'll say, oh no, it's variables and functions. Okay. The key concept here is that those attributes, it's all about information hiding, that those attributes should be related to that class and that class only. Okay, so they're an attribute. By the way, the word attribute means sifa, an attribute of that class. And the operations are the operations that are done by the concept represented by the class name. And like I was saying before, a lot goes into a class name. So if you give a confusing class name, you're really making it hard for your development team to tag along. All right. Between those classes, there are three types of relationships that we're going to focus on. Okay, actually, four. Okay. Associations. Next up, aggregations. Third, composition. And fourth, generalization. Okay. And again, generalization in the UML modeling world, in the programming world, they call it inheritance. Good job. Yes. All right. So association is the most basic of all these relationships. And they are like the vanilla type of of saying the least and committing to the least. And all there is saying there is some association between that class and this class. I'm not going to say any more than that. That's really how far it's going. Okay. It's just saying that there's going to be some communication between them. I'm not sure what. Okay. So if you want to be least committal, you use the association relationship. All right. Obviously, our goal is to be more descriptive and more specific with our relationships. So in situations where they can be a chance to use more a specific version of a relationship, then we should, rather than using association. Okay. For example, car and a vehicle. Those two concepts, there is an association between them. Okay. I could just draw a solid line and say, well, yeah, they're going to be related from somehow, okay? But are we better off, and are we doing everybody else a service, had I put down inheritance, or should I say generalization, instead of association? All right, so I think I already covered that. So association, the notation of it comes as a solid line, okay? For example, in this slide over here, I'm saying that I have a patient and a patient record, and then there's an association between them. Every patient should be having a patient record. And that's really basically all there is to it. And for every patient record, there is a patient, okay? And notice how I actually said that. I'm actually looking at it from both perspectives, because I said patient has a patient, should have a patient record. And I also said at the same time, a patient record has a patient. Really, what I just said right now is a bidirectional thing, okay? It's called navigational direction, okay? So I can navigate from patient record to patient and from patient to patient record. Next up here, for example, a little bit more information. I got an order, a class called order and a class called customer, okay? And you know that this is a directed association because the line has an arrow at the end, okay? So in this design, we can look up a customer using an order, but not vice versa, okay? For some reason, I know it's probably not a good design. It's probably a customer should be able to look up their orders, but you know, what this is saying, that order can see customer, but customer cannot see order. Now, if I'm at class order, what I would have use that variable inside the code of class order to say customer.print name, as for example. Now, class customer would not have a variable of type order. So there's no way you can access any information inside class order, okay? I know in a realistic setting, it's probably not silly because you should be able to look up an order from a customer, but you get the point, all right? Now, if this, for example, was, I said, for example, professor, and this is student, what does that mean? Now, what does that mean as in terms of the capability of a search? Can I find every professor's students, or can I find every student's professors? Exactly. So this is what that would mean. The view, the navigation is unidirectional. Okay, it's directed. We call it directed relationship association. And it just says that, yeah, the professor can see the student, but not vice versa. You can't look it up the other side. All right. Now, the association relationship itself, as a concept, it can have on its own attributes. Okay. The first of which is that it itself, as an association, can actually have a name. Okay. So I have a class called employee, another class called department, and the association that I've created has a name called is member of. And I put that little play button arrow, okay, the black play button arrow, kind of like to tell me how should I read it, that an employee is a member of a department, okay? Now, this is a member of thing. It's not the name of the employee. It's not the name of the department. It's not the name of the man. It's something describing the association itself. In other words, it's actually describing the nature of, okay? So if this was professor, employee was professor, and department was student, what would be a good name for that association? Teaches, okay? All right. Now, teaching doesn't define me as a concept of a professor. It doesn't define you as a concept as a student. But it's only when we get together that this teaching thing is actually happening. Okay. Another thing that we can do with association is that we can define roles of the association ends. Okay. So at the bottom part over here, you see from employee to manager, I'm actually defining the roles of what those classes are and what they are playing as a role in that association. So the way I read it is that in the association between employee and the manager, okay, that the manager is managing, okay? So manager manages, okay? Whereas the employee is managed by, all right? This one is a little bit too direct. However, you know, you could have had that this, for example, is a situation where I'm at a restaurant and for some reason the class that is written is, say, مثلا human, okay? Another class, a class called human, and that human is playing the role of customer, all right? Obviously, you would probably have a class called customer to begin with, but if that role in itself is not defining what that class is about, and it's only relative when that association is in play, then I want to put that role, okay? So again, professor, student, okay? My role would be teacher, okay? And the student would probably have a different role, okay? Trainee, for example, something like that, all right? Yeah, actually, that's a good example, right? Like a company and a student where you're doing your internships, okay? So they got trainer and they got trainee or internee. Is that even a word? I'm not sure. Intern, yeah, intern, yeah, probably intern. Now, but that's the key part. Being an intern doesn't define you as a student. It's an aspect of you when you've come to be, matter of fact, it's an aspect that you never even noticed existed in the first 2 years, even 3 years of your life here as a student. It's only when you hit the summer of the third year when you realize, hey, wait a minute, I'm an intern, all right? What I can also do is I can define multiplicities for those associations, okay? Now, before I go into this slide, I wanna just step out for a second. Where is it? Oh, wait. No. Sorry. All right, here we go. I need to just make sure I share the screen. Okay, so sometimes you'll see something like this, okay? Class A, all right? And class B, okay? And you'll see something like, say, 1 to 3, okay? This right here, those numbers are what we call the multiplicities, okay? Now, what actually, and this is very important for you to understand, what actually is running And what actually is executing in any system is not classes. It's objects, okay? Classes only when you use the term what? The keyword? Somebody tell me? No. Abstract, matter of fact, the absolute opposite, yeah, it was. Okay. Huh? What is the keywords? Guys, wake up, wake up, wake up. Keyword, yeah. Okay, so I said what's actually running in a program is objects, not the actual classes which you see in front of you on the screen, which you actually code. Because what you write at the top of that code is class student, right? You don't write object students, okay? And what actually runs is the object that you've created when you hit the keyword new, okay? Student S equals new student between brackets, okay? All right, yeah, Java 101, all right? Right. Now, we liked when we pride ourselves and the object-oriented community prides itself in that it's objects that are running, not the actual class. But however, there is an exception to make code in a class itself run. How? Say what? No. Oh my God. If we should have just probably just canceled that class and waited until after. Yeah, code in a class in itself runs. Yeah, but how? How? Because you're written code, right? Huh? No, I'm talking about a keyword. Tell me the keyword that makes the actual code in the class run. Keyword, just one word. Starts with the letter S. No, not super. Super is to say, static. Like, okay. Since we're in that situation, I'm gonna have to step out of this lecture. Okay, guys, and guys at home, what I'm gonna be talking about is not part of this course, okay? Okay, but it's important for this course, so, but that's fine. I was expecting this was gonna happen, but so that's fine. Like, when you actually write code, this is what you see in front of you on the screen, okay? And, you know, you got a class up called مثلا class X. Okay, this is class X. All right. You write down variables, for example, variable A, B, C. You write down functions, function D, E, F. Follow me so far? Now, this is you sitting on a chair, doing the programming on the keyboard, and this is the physical reality that you see. What actually runs is not this, okay? It is something called a Java virtual machine, okay? Now the Java virtual machine, what it should be running is just the object. Now, at some point when you go like this, X, small x equals new, what is this line doing? Please tell me no. This is music to my ears. So everybody's super confident now, okay? Good. What is the name of that variable? Small x or a big X? Oh, X. With Dalil, if I go X, Y like this, new X, what is this line doing? Exactly, I'm creating another object, right? And this is why when I want to call up on that object, I want to print its value of A, I would actually write down X dot A. Okay, I would write Y dot A. Okay, what's really actually happening is that when I create an object of that file that I've created, it makes a copy of everything it has. So here it's got X, okay, and it goes A, B. It's got its own version of A, B, and also the functions D, E, and F. And then Y has the same thing, A, B, D, E, and F. Okay, that's when I run into my Java virtual machine. Okay, guys, phone's down just for a moment. Okay, fine. When I put this magic, lovely word saying static. Okay, static on a variable or a static on a function even. Yeah, but what does that actually mean? Okay, that means when I'm creating those objects, X and Y, okay, I am not getting a copy of C and the function F. I'm not getting here C or the function F. If I go at some point and say, please go ahead and print for me X.C, can I give you an error? It says I can't find V. From Java Virtual Machine's point of view, it doesn't see the C for the objects. Okay. Now, the funny thing is that because I did put the word static in there, okay, it's actually has the big X, only one of it, okay, and that big X has all the static and only the static variables, okay, meaning that from the Java Virtual Machine's point of view, just running out of battery, okay, it's, I have a class called X, and it only has a variable called C and a function called F, okay? X dot A error, okay? Because it doesn't see it. It goes to the objects. It doesn't see it, okay? If I go X dot B, same thing. If I go Y dot C error, doesn't see it, okay? It's all about the perspective of the Java Virtual Machine, what it is actually seeing. Now, you write it in one place, over here, all right? The things that are not static goes to every object that you create, whereas the class itself, it only has the static variables on the static point. In other words, had we not put anything being here static, it would have actually seen the class X and it would have seen absolutely nothing inside of it, okay? Now, finally, this is the reason why, after all these years, the reason why you've been getting this error that you could mystify you saying non-static variable cannot be called from a static, stupid context. And you're like, why is it doing this, right? And all you can see is you have a big, something like this, student.name, right? And let's face it, we've all done this. And they give me a little squiggly red line underneath it, okay? You give it a right click. It suggests that you do a small, you say, wallah, okay, fine, make it a small letter S, and then suddenly that red squiggly line is gone. And you're saying, I don't know what just happened over here, but the error is gone, it's compiling, it's running, I'm gonna submit now, right? Halab al-Khamis, right? Now, does everybody understand why you're actually getting this error all these years? All right? All right, good. Now, I know I diverted quite a bit from the actual lecture, but I don't mind. Yeah. Now I remembered why I diverted, okay? So here we go, we got A, we got B. Oh, no. Okay, there's an association between them. Now there's a multiplicity. For example, 3 and 1. What does that actually mean is that the instances of those objects of those classes being associated with each other has to be in accordance with this multiplicity. For example, when I see an object B, it should always be connected to 3 objects of A. No more, no less, okay? We do have our flexibilities to say yes, more or less, including 0. 0 means that I could have had B on its own. had this 0 not been here, every time I saw a B, it must have been connected to some A object. It's almost like proteins and things like that, where they connect with each other and the atoms and all that stuff, right? That's the way it is. But the 0 lets me know that I is going to exist alone, at least when it comes to that association with that particular class, A. Okay. Now, يعني مثلا I could have said مثلا 0 or 1. Okay. 0 or 1 means this is okay. It means this is okay, but it also means that this is definitely not okay. All right. So this 0 gives me an option to make this whole thing go away. Yet at the same time, if I had a class called in like a 1-to-1, then each one of those has to have a C. Good. Good stuff, right? Let me just erase this. Where is it? Are we going back to this one? All the time just went flying by in this lecture. Right. Up. Where is it? And with it, I can start to define many different types of multiplicities. I can say that a company has 1 president, okay, by putting the number 1. Okay, a bank manages an account, 1-to-many. I can have a many-to-many, a course and the student. Every course has many students, and every student has many courses. I also have a, well this is not, okay. Well, let's just stop it for now. All right. Now, when I'm looking at this, what does this mean? It means that every customer can have multiple orders. N means not 1-to-many, but 0-to-many. Okay. If I want to say many, but at least 1, I got to go 1, ... and we're going to talk about these denotations in a moment. Now, on the other hand, every order has a maximum of not just a maximum of 1, but also a minimum of 1 as well. In other words, there's no such thing as an order without a customer. Okay, so sometimes it's good not to have that 0 in there. Okay, it just doesn't make sense that there's an order without a customer. صح? Why are you looking at me like mystified? Like, no, I've seen it before. There's many orders without customers. All right. Here's the 1-to-1 situation, the patient and the patient record. The patient record obviously exists for 1 patient. The patient should have just the 1 record. Okay. Kind of like that Seinfeld episode. I'm reading it. For every order, there's 1, no more, no less customer. For every customer, there can be 0 orders, 1 order, or many orders. Okay. This is the notation. N, or the asterisk, means many. It actually means the same thing as 0 to N. So it's not common that you will find 0 to N because it's already implied. It just means 0 to N, really. Okay, it means any number. Basically, N is a joker number, just like the asterisk. 1 to N, many, but at least 1. Now, if I need to define a particular number, say, 1, 2, 4, 7. So 3 is not allowed, 5 is not allowed, 6 is not allowed, 8 and more is not allowed. Okay. If I want to define a range, I put the ... thing, which I've used. So 1, 2, 3, I can do that with 1, ... 4. Finally, I could do a hybrid of all of those if I really want to. So I can say, well, 1 is allowed, 2, 3 is not allowed, everything from 4 to 8 is allowed, 9 is not allowed, and so on and so forth. If I really want to, I don't know what sort of situation would prompt or require such a, but in case you want to, it's there. You didn't, I didn't ask you for multiplicities. Okay. Now, remember I said before, the way I'm going to mark it this time is different. Now, had I brought you the same question at the end of the year, I would have expected to see the multiplicities there. I would have been a nice chunk of your mark. Okay. But now I don't look at it whole. Like it doesn't even count. Say what? Oh, you volunteered to add the multiplicities? We didn't cover that just yet. So anyway, no harm, no foul. Now, here's the thing, okay? I can have association. It defines the relationship between two or more classes. An employee, for example, works in a department. We've already seen that. I think this is, yeah, there's a couple of slides here that are repeated. Okay, this is why I got. Okay. Anyway, numerical specified association, car has a door, and if you one door, two, like اثنين باب, أربعة باب, four door, five door, and so on. Optional, customer maybe owns a debit card, maybe not. Okay, so it doesn't have to be. Okay. Actually, let me stop over here. Let me see if you really, really get this. Okay. Now. Okay. What? You're not getting off that easy. Okay. Now, guys, I'm gonna ask you something. Okay. And let me